So we study derivatives because they are useful. So let's start seeing applications of derivatives. For example, let's say we have the function f of x that is x to the power 4 minus 2x squared, okay? And we want to find all points of the graph with horizontal tangent lines, okay? Now, if we can plot it, then it's very easy, okay? We will be able to spot those points, but if we are not able to plot it, then how do we find those points? Well, we saw that horizontal tangent line means that the derivative is 0, right? So then what we want to find here are points x such that the derivative is 0, okay? The slope is horizontal, the derivative is 0. But then we can just compute the derivative, x to the power 4, the derivative is 4x to the power 3 minus then 2x squared, the derivative, right, is 2 times the derivative of x squared, which is 2x. So that means, well, let me just write it, the complete thing. So this is equal to 0. So we have 4x to the power 3 minus 4x equals 0. Okay, and that gives x to the power 3 minus x. That's x times x squared minus 1 equal 0. Okay, so here we have three possibilities. We have x equals 0 is one possibility, and the other two possibilities, right? Because this is x times x plus 1, x minus 1. The other two are x equal 1, x equal negative 1. So these are all the points where the graph has horizontal slope. Okay, this is something we will be using a lot. Okay, the other application I wanted to discuss was how to find instantaneous velocities or accelerations. Okay, we saw already that that's another interpretation of the derivative. If a function f, like this one, that we have here 60t minus 6t squared, okay, a function like this, there. If a function like this describes the movement of a particle, of a car, then the instantaneous velocity at a given time is given by the derivative. Okay, that's the rate of change of the position. So let's take note of that. The position at time t is given by f of t, which is 60t minus 6t squared. Okay, the velocity at time t, that is the rate of change of the position. Rate of change of the position is f prime of t. And then the acceleration that the problem also asks, acceleration, that is the rate of change of the velocity. So that's the second derivative. Okay. All right. So yeah, so let's compute the derivative. The derivative is 60 minus 12t, and then the second derivative is minus 12. Okay. So that answers the problem. So part one, find the velocity at time t. That is given by this formula, 60t minus not this one, this one formula, 60 minus 12t. That is the velocity. And then the acceleration is given by the second formula, the second derivative, it's negative 12. Okay. But then there is a third question. How far does the car go before stopping? So this would be 1, this would be 2, then 3. How far before stopping So for that, we need to understand what does it mean to stop. Okay, when is the car stopped? Car is stopped. Well, you could say when it's not moving, right? But that means that the velocity is 0. So if the velocity is equal to 0. So what we want here, because we know the formula for the velocity is here f prime is 60 minus 12t equals 0. Okay. So that means t is going to be 60 divided by 12, which is 5 seconds. So it's not asking when is the car going to stop, it's asking how far before stopping. So we need to plug this in the formula for the position. So f of 5 is 60 times 5 minus 6 times 5 squared. And this is 300 minus 150. So that's 150 feet. This is how far the car will go before stopping.